Hi, my name is Shrivant Reddy, and this is my lab on constant velocity. For our introduction, we observed that our object, in this case a marker, was going at a constant velocity, and we analyzed this using a video tracker. We used a meter stick and put it against the marker in order to use a visual reference to track how the marker and how far the marker went in our video. And in order to mimic this motion, we used a computational model in GlowScript in order to better understand the second law of motion and momentum. For physical principles, the main ones that we used were Newton's second law and the momentum principle. Newton's second law states that force equals mass times acceleration. But because because we're observing constant velocity, we are to assume that acceleration is zero. Therefore, F net, or the total net force, is zero in the x direction. Because of this, we can also say that because F equals zero, then change in P is also zero. So there is no change in momentum. Therefore, we can conclude in both cases that there is zero acceleration and no net force in the x direction. And we were able to put this in GlowScript and track that. Here's a video of us using the tracker on our marker. As you can see here, we set up the boundary lines and the marker follows this line here. And we use these points to track each time interval at which the marker passes. The results that we gained from this is that the average velocity was 0.231 meters per second in the x direction, and the marker traveled zero point 0.9 meters in 3.9 seconds. The graph here, position over time, was given to us in GlowScript. And as you can observe here, that it is not a perfectly straight line. There is a curve to it, meaning that not all of it was constant over this time. This is because of the other forces that are acting upon the marker, such as friction, air resistance, and other things. But because we are to assume that this is negligible, and that's why our results are kind of flawed. And as we will see further, we will see a difference between our experimental results and our um, actual results. For a computational model, we said that the ball position was at 0.00164 meters, and our ball velocity was 0.257 meters per second in the x direction. Our time started at 0, delta t was 0.27, and our final time was 3.9. We also incorporated the velocity update and the position update formula. As we could say here, that F net was 0, so therefore, because the force was 0, then velocity would not increase. And therefore, we could say the velocity of final would be velocity initial. The vector, because vector was 0. And because the velocity was always constant, the ball position, ball final, would always equal ball initial plus the ball times delta t. So we would observe a constant upward trend. As we can observe here, this is the ball that we have, and this right here, the straight line, this is our computational model, and this is our experimental data. Though they're quite similar, this discrepancy is highlighting the differences in the experimental environment. One in a computational, assuming no friction, no errors, nothing else. So there's always a perfect zero net force. While while in reality, there's always some forces acting upon the marker, whether it's some friction or air resistance. Our final questions that we have is that how would the results change if we were to flip the axis For example, if plus x and x minus x were interchanged, what would happen? And what forces are added together to produce a net force of zero? Thank you. Thank you for listening.